This talk is based on a paper that I published in the International Journal of Market Research in 2016. And it's attracted a great deal of interest in the market research community. It's had thousands of reads on ResearchGate. So sample surveys are one of the main methods by which data are collected for statistical purposes around the world, in particular by the Office for National Statistics, and where I worked for many years, and also in my later career when I was working for Kantar, world's largest market research firm. And results from sample surveys always need to be weighted to produce unbiased estimates. Most obviously, if it's a sample survey, you need to gross it up. And you might think, well, that's easy. I'm sampling one household in every 1,000. So you just take the results, multiply by 1,000. But there are many complications with this. The first one is that your sample you've drawn might not be exactly representative. And secondly, that everybody you try to contact, sometimes you can't get hold of them, or they refuse, or they give you a rubbish response. And if the non-respondents are totally at random, that doesn't really matter. But if they're systematically different from the ones who do respond, you've got a problem. So in my experience, the ones who are least likely to respond are one-person households, youngish males, or 20 to 39, and to a lesser extent females, 20 to 29, and people with very young children. Of course, these categories overlap. A lot of one-person households are young adults, and a lot of people with very young children are young adults. So how can we reduce this bias? You go to the official government statistical office, and how cooperative they are and how cooperative they can be varies tremendously from country to country. In some countries they haven't held a census for years, and even where they have had the census, it's not very reliable. But in this country, we're very well furnished. We do have an excellent census, and got good data from other sources. So we ask for population by age and sex. If it's a large country, we ask for population by region. And we ask for number of households by size. And I say households. In many surveys, we're only interested in people who live in households. We exclude people who live in communal establishments, which might be prisons or army camps or hotels or student hostels. So if we're just concerned with households, it makes life slightly easier. And when we weight, each respondent ends up having a weight. And the idea is that if we take some particular group of people, say males aged 5 to 9, and we add up all the weights for respondents in that category, then we get the known number of all males aged 5 to 9. Now, there are various ways of doing weighting. For best results, we want the sum of the squares of the weights to be a minimum. And I'll explain in a little while why we want this condition. Now, with a perfectly balanced sample, it's a well-known elementary result in statistics that the variance is proportional to the reciprocal of the sample size. But if the sample is not perfectly balanced, we can weight it. Then everybody's got a different weight. And the variance is larger than with a perfectly balanced one of the same size. And the efficiency of the weighting is defined as the variance from a perfectly balanced sample divided by the variance from the actual sample, expressed as a percentage usually. And since the variance is always greater than from a perfectly balanced sample, the efficiency is always less than 100%. And the efficiency depends on the reciprocal of the sum squares of the weights. So the smaller this sum, the higher the efficiency. So in other words, if there are various different ways of doing the weighting, if we can find a way that minimizes the sum of squares, that's the best way to weight it. Now, it's been known for a long time that there's a simple method that can calculate the weights in one step. But there are two problems. It involves multiplying and inverting some very large matrices. If you've got, as in one survey I dealt with, tens of thousands of respondents, then you have to invert a matrix that's tens of thousands by tens of thousands. It's also possible for some weights to be negative. And it's ridiculous. You're saying that if you add this person to your sample, it actually reduces the amount of information you have. Now, Deeming and Stephan in 1940 proposed an iterative method, and they called it RIM, which stands for Random Iterative Method, which is slightly confusing because the controls for the weighting are also called the weighting rims. And they thought that their method converged the exact solution you get by a matrix inversion, and it doesn't. It is better than it cannot produce negative weights. But it often produces a significantly larger sum of squares of weights than the exact solution. So, can the method be altered to give a lower sum of squares of weights, but still avoid negative weights? Another issue that arises is that sometimes, if the sample is very badly unrepresentative, some weights may be many times larger than the average weights. And some clients don't like that. And the traditional solution to that problem is weight capping, which is that no weights are allowed to be more than, say, 4 times the average weight. So if you do your weighting and you find you've got some very high weights, you trim them down to 4 times the average weight, and then you have to adjust the weights to add up again. I disapprove of capping. Sometimes, in extreme cases, it stops the iterative process from converging. Also, it can cause a bias. People with high weights are likely to be similar. So typically, the highest weights are all for males aged 20 to 29 living on their own. If all the weights for this group are reduced, results of the group will be underestimated. So, can we tweak the Deeming and Stephan methodology to minimize this issue? So first of all, I have to explain how rim weighting works. If you've got a set of numbers, x1 to xn, we can create a set y1 to yn with a given total t by simple multiplication. You calculate t over the sum of the x's, and you multiply all the x's by this factor. And if all the x's are positive, then obviously the sum will be positive. So this factor will be positive. So all of the y's will be positive. Now, you have to, with this method, start by giving each individual in the sample an initial weight, which is usually 1. So that's all positive weights. At each stage, you adjust these weights by this method, so weights can never get negative. So let's take an example. So the first rim is the area of the country you're in. There are 5 areas. Respondents are classified by which area they're in. So you get the results here. And the universe, which is the population you've got from the Government Statistical Office, is given in the next column. So you divide the universe in each area by the number of respondents in each area, and you get a weight. So now you take the second rim and say it's got 3 cells: adult males, adult females, and children. Respondents are classified into these 3 cells. The respondents are now no longer all have the same weight, because ones in different regions have different weights. So we'll take the sum of their weights, and the results might be like this. We've got the same number of respondents, but the sum of weights is no longer equal to the number of respondents. And the universe is now not the population of an area, but the population of males, females, and children, respectively. So again, dividing the universe by the sum of the weights, you get a weight adjustment factor. So to get a second set of weights, you multiply the first set of weights by the adjustment factor. So for an adult male in area 1, the initial weight is 3.4324, and the adjustment factor is 0.9509, so you multiply them together. And similarly for the weight of a child in area 2. So you've now got 15 possible different weights. And you now do the same thing for each rim in turn, how many rims you've got. And when you've gone through this cycle once, 2 respondents will only have the same weight if their demographic characteristics on all the rims are the same. So you might say they're 2 people of roughly the same age, living in the same area with the same household size, or whatever your rims are. Instead of doing a multiplicative adjustment, you do an additive adjustment. You take the total you want the x's to have, you subtract off the total they do have, and you divide by n, the number of observations. So if you add this to each of the xi's, then again the yi's will total correctly. And if you use this additive adjustment consistently, this does converge to the simple matrix procedure that I mentioned earlier. So why don't we always use this method? Well, the answer is, if the total is greater than the sum of the x's, we're increasing the x's, and the resulting y's will have a smaller standard deviation with the multiplicative adjustment, reducing the sum of squares. So that's very good. They will also have a smaller maximum than with the multiplicative adjustment. So that reduces the problem with very high weights. However, if the total you're trying to adjust to is less than the sum of the x's, you're decreasing the x's. So you get so your results will not be as good as from multiplicative adjustment. And what's more, sometimes the adjusted values, the yi's, could be negative. That can never happen with a multiplicative adjustment, but it can happen with this method. So that's why additive adjustment is not used. But then I came up with the idea of asymmetric weighting. It's obvious when you see it, like many good ideas. It uses both the additive and the multiplicative methods. Use the additive method when the x need to be increased, when it's better than the multiplicative method. The multiplicative method when it needs to be decreased. So we get the best of both worlds. We get a lower sum of squares, and we never get a negative weight. And you might say that's very well in theory, but can we prove it in practice? And I've tried this on a number of data sets, and at least for those sets, the efficiency is improved because we've reduced the sum of squares. Also, the number of very high weights is reduced, which, as I say, means there's less capping of weights needed if the client does insist on weight capping. As a downside, it usually needs rather more iterations, so it increases the time it takes to do the weighting. In my experience, this isn't a serious problem. With the data sets I've been using, it might mean it takes sort of 7 or 8 minutes rather than 6 minutes. Not the end of the world. Now, you ask, how does the distribution of weights change? Now, the sum of the weights must equal the total universe being controlled to. So the total of the weights is the same in both methods because you're controlling to the same total universe. And as I say, the largest weights will reduce. So it might be thought the smallest weights will increase. And much to my astonishment, the smallest weights tend to be smaller. I can't explain this. It's just an empirical fact. The weights that increase most are those around about the 80th percentile, going from the smallest weights to the largest weights. So these are some surveys that I was responsible for in Switzerland. This is when I was working for Kantar Media, and we were monitoring how many people watch television in Switzerland. So as part of that process, we did a big household survey to find out how many people have televisions, how many people have more than one television, and a few other things that you can't get from the official statistics. And you see there were 4 surveys in 2012 and three surveys in 2013. One of the 2012 surveys, we had controlled it to old data on the population. Then we got revised data which were significantly different, so I redid it. That's why we've got 2 lines there. So you can see that in every case, the efficiency has gone up slightly. It's not miraculous. It's not the efficiency has doubled or anything, but it is a worthwhile increase. And here we see the effect on the weights. And you can see that the minimum weights have all decreased, and so have the maximum weights. And in Switzerland, actually, we didn't use weight capping, but if we had used weight capping, it would have significantly reduced the number of weights that needed to be capped. And you can see it does require more iterations usually, but not a vast number. And then that was all I had when I first started giving this talk. But then I also dealt with a survey in Georgia. That's the former part of the Soviet Union, not the state in America. So completely different country, completely different weighting strategy needed. But again, you can see the minimum weight goes down, the maximum weight goes down, the efficiency goes slightly up, and the number of iterations goes up. So exactly the same results as for Switzerland. And that's the paper where I explain the method in detail.